Hey y'all, I am setting up and I'll be with you in just a couple minutes. Okay, if I could get a show of hands, you should be able to see my screen right now and hear me. If you can you raise your hand, please? Okay, perfect. Looks like y'all can see what's going on. I'm not streaming video, camera of me, just because for bandwidth purposes, I want to make sure that with me streaming my laptop contents that everything goes pretty smoothly. So today is our second week dealing with design of a relational database. Last week we were talking about a technique called entity relationship modeling that is a top-down approach to designing a relational database. This week we're going to talk about normalization, which is a bottom-up approach to designing a relational database. And we often use the two hand in hand. I'll show you when I get to the slides. There were just a couple things I wanted to mention before we get to that. First of all was the answers to one of the questions on homework 2. On the first question on homework 2, you were asked to list the details of all rooms at the Grosvenor Hotel, including the name of the guest staying in the room if the room is occupied. And some of you did something that was very subtly incorrect, but had important ramifications. And that is, when you were checking to see if a room was occupied, the correct way to check to see if a room is occupied is that the date from is less than or equal to the current date, and the date to is greater than the current date. Many of you wrote greater than or equal to the current date, but that is not correct, because I had said that when the day you check out is not considered to be a day that you are occupying the hotel room. So for example, if the date 2 is 2021 02 23, then the person is not considered to be occupying the room on 2/23. They're checking out that day. So the room is considered to be unoccupied. So that is why you have to say that the current date is greater than date 2, because if it's equal to date 2, it's considered unoccupied. And to further show you why it's an issue if you're using greater than, suppose that Bugs Bunny checks out on 2021 and that Wile E. Coyote checks in on 2/21/02/23. Then if you're using this particular thing of date from less than or equal to current date, you will sweep up Wile E. Coyote because Wile E. Coyote's date from is less than or equal to current date. And you're going to sweep up Bugs Bunny because Bugs Bunny's date 2 is greater than or equal to the current date. So technically, which person are you claiming is occupying that room? Is it Bugs Bunny or Wile E. Coyote? Because according to your query, the way you wrote it with greater than or equal, both guests are occupying that room. So that's another reason why greater than or equal is not right here. You have to use greater than. So just wanted to point that out. I think I told Bhaskar to deduct something like 3 points if you said date greater than or equal to, because it was an important, even though it's just a small mistake, it has important ramifications. The second thing I wanted to point out is that there are times when you may remember that I have the booking relationship. And it was a three-way relationship between hotel, room, and guest. And I was having some difficulty always coming up with multiplicities for when a for the room multiplicity. And the reason I realized that I was having difficulties is that when I was thinking about room multiplicities, I was looking at I was saying, okay, for a given guest number and a given hotel, I was thinking how many room numbers can be associated with one guest and one hotel. And that was the wrong way to be thinking about it because, in fact, a room is a weak entity that is associated, it's a weak entity for a hotel. So it depends on a hotel for its existence. And in fact, a room is not just a room number. A room, my mistake was that a room is actually a room number and a hotel number. That's what the entity is. It is a room number and a hotel number. That's what the primary key is as well. So the actual question should have been for a given guest, how many rooms at a could that how many a second it really was for a given guest number, how many rooms can be in that relationship. So the fact is a guest can rent one or more rooms at a particular hotel. So the answer should be 0 to many because it can rent 0 to many rooms at a particular hotel. And I also realized that while this is one way to show the relationship, you could also, in some sense, write it as just guest, whoops, Yeah, guest. Books, room, and then a room, we kind of have a hotel provides rooms. So I would not be unhappy if on a homework assignment, if you have a weak entity and a strong entity, here the weak entity room, here the strong entity hotel, if you just have the relationship between something and the weak entity and not necessarily including the strong entity. Now, this also is fine. And in fact, I think does this tertiary relationship better shows how a guest books a room at a hotel. But I can see where this is okay too, because it's a little easier than to figure out the multiplicities. So I'm going to accept either answer in the future, just because, as I said, the principal relationship is between the guest and the room, and that encompasses the fact that it's with a hotel, because the room includes a room number and a hotel number. So questions about that?
For the booking relation, just out of curiosity, the room number and hotel number you were saying were the primary keys, but I was also thinking the entities within booking relation. It's a relationship relation.
Yes,
Wouldn't guest
booking's a
number also
relationship.
be? Yeah, yeah. Wouldn't the guest number also should also be a part of that key, because doesn't it depend on the guest number as well, not just the room number in the hotel,
Yeah,
but
actually, you're right. It's only part of the primary key.
I was just
Yeah,
curious.
actually,
Okay.
the if when we went over it, it was actually room. There were multiple potential keys. There was room number, hotel number, date from was one possible key. Um, then you could also have room number, hotel number, date to is another possible key. You also had guest number and date from there as a possible key. So it turns out there are 4 potential candidate keys for the room relation, for the room entity. So you don't actually, guest number and room number, hotel number form parts of different keys. They're not part of the same key, but you are
Yeah,
right. Guest number, room number, and hotel number by itself do not are not enough to form the primary key.
yeah. Now that I think about it, it is possible for, like, if they keep the same, like say the guest comes at a later time and gets the same room at the same hotel.
Exactly.
If
Yes.
that was just your primary key, you'd see it twice.
Yes. Exactly. So it's kind of like, but this also right here shows you what's going on. It's kind of like, okay, here's one key, here's the other key and part of the key. And hence that is why you could think of it just as a binary relationship between guest and room, rather than having to drag hotel in as a third um, one. So as I said, I'll accept it either way, as a tertiary relationship or as a binary relationship. I
Hope you
just
don't mind if I try to turn everything into a binary. So much easier for
Well,
me to
that's
wrap my head
fine, but
around.
there's going to be times when it really is tertiary. So yes, I don't, if it really is, I know it's a lot easier to think of things as binary, but there are times when it really is tertiary, and then you will get points taken off. So you just got to be careful. This is a kind of special case, because room is a weak entity for hotel and hotel is the strong entity. So it just so happened that as part of room, it has the hotel attribute in it. So I totally understand. It's a lot easier to think about binary relationships. Just if something does turn out to be tertiary, you have to be ready for it.
Would you say that we could have identified, sorry to keep going on this, but we could have identified this problem with booking by noticing that all the primary keys from the other relations, the base relations, they were not unique. They could not be formed just by themselves to form the primary key of the relationship relation. Does that make
So
sense?
that tells you that it's a relationship. So your observation is a good one. So if it turns out that just one, if you have multiple keys to other relationships and one of them, I'm sorry, multiple keys pointing to different entities, and none of those keys is unique, can be used as the primary key by itself, then you probably have a relationship. It's
Okay. Well, I was thinking in terms of like if I take the primary key, like, in this case with booking, there's three entities and they all have a primary key, which is room number, hotel number, guest number. And the fact that when we looked at booking, the first thought would be take all those primary keys, combine them into um, a primary key for the relationship itself. And the fact that that didn't work, should that have keyed us into this weak entity problem and that you can turn it into a binary? It's kind of a fairly loaded question.
no, actually not really, because in in general with a all it told you was that the relationship was not a one-to-one, that there was some one-to-many aspects to it. That's all that it told you.
Okay.
It didn't tell you the fact that putting them all together, if it had given you a unique thing, it would have told you there was a one-to-one. It would have told you something about multiplicity of the relationship. It wouldn't have
Okay.
told you anything about the fact that there was this strong versus strong weak entity portion to it.
Example that we did the case study from last time, and I was able to come up with a bunch of binary stuff that looked like I didn't look at the key. And I came up with a bunch of stuff where there was a bunch of relationship tables or relations, and it was all binary. And to me, it made sense. But then, of course, I look at the key, and there's this tertiary, or maybe even more.
You mean
Um,
are you talking about the investment study?
yeah, yeah, that last one we did.
Okay, let's
Where
take
is
a
it?
quick look
Yeah,
at
the
that.
investment firm design.
Okay, so right, I came up with this. Okay,
I
so
came up with a bunch of binary stuff. Like I was able to make just different entities. I missed a couple things, but it looked to me like it could be divvied up with more. I mean, you had several binary relationship tables.
okay, so this is where I would take off if you came up with binary relationships. This was a true tertiary relationship. Okay, here there are no weak entities. Advisor, investor, and stock. They are not, none of them is a weak entity. So this is a true tertiary relationship. And if you go back and you look at the particular stock transaction here, right here, you do see that there are three foreign keys: investor number, advisor number, and the ticker. And those are foreign keys into, the ticker is a foreign key into stock info. Investor number is a foreign key into investor info. And advisor number is a foreign key into advisor. So there it truly is a true three-way relationship. And you'll notice that there is no, in each of the three relations in question, there's so in room there was two attributes that form part of the key. It was room number and hotel number. That's part of the tip off that it might be a weak entity. Here, there's no such thing going on. Investor info, advisor, and stock info are all uniquely identified by a single attribute. So my guess is you tried to do something where you said maybe that an a advisor, we maybe have to take this up offline, but I'm guessing you might have done something like
Yeah.
an advisor transacts something for investors. You might have had some other binary
Well, there was
relationship.
another one like advisor manages office or something like that too.
Why don't we
So maybe
take this
maybe
one
that's,
offline? Okay, I think I'm going to have to
yeah,
see what you want it to do, but
yeah,
I do want
never
to
mind. Yeah.
I do want to emphasize that this was a true tertiary relationship. There was no way to make this one into, well, you could try to make this one into a number of binary relationships, but I would definitely deduct points because um, here there's no weak entity involved in this relationship.
Okay.
Okay, so this is only a situation that arises is a special case where both a weak and a strong entity seem to be involved in a relationship. And in that case, I'm okay. What I'm saying is if the relationship involves both a strong and a weak entity, like here, I'm okay with your either showing it as a tertiary relationship or as a binary relationship where you just are in a relationship with the weak entity.
Okay,
That's
that
a
makes
special
sense.
case. Okay. So actually, I think I do need to move on. So I can kind of get through normalization today. But I'm happy to take some questions after class. So let us get to that. So normalization is a mathematical technique. It's an algorithm. So top-down design using ER diagrams is a subjective exercise. It's really based on judgment, and you could well argue that there are multiple ways to do it. Normalization is much more mathematical. There's much more a right and a wrong way to do it. It's you can basically specify a mathematical algorithm for it. So it's essentially a mathematical way to decompose relations into uh, groupings of logically related attributes based on functional dependencies. And generally, what you're doing is you're decomposing into entities, but we're going to see sometimes that is decomposing into a multi-valued attribute or something else. And it is attempting to minimize the likelihood of introducing inconsistent data into the database by minimizing redundancy. In particular, what it's trying to do is normalization is trying to ensure that descriptive attributes are only stored once. So you'll remember I said there's three types of attributes. There's descriptive attributes, there are identifying attributes, which are essentially keys. Okay, and then there are linking attributes, which are foreign keys. So these are linking, which are foreign keys. So we can't avoid repeating to have some redundancy right here. So there's going to be redundancy here because a foreign key has to be the same as some identifying key. But we're trying to attempt with normalization to only put a descriptive attribute in one place in the database. So that's the goal. And here's the figure that I kind of wanted to show you that shows how you approach design in general. So you can have either this top-down approach based on ER modeling or a bottom-up approach based on normalization. But over here, this gives you a good idea of how you are obtaining your information that you use to design the database. So you talk to users and interview them, and they give you some requirements. Then there is, so that's one way you get information. Another way you get information is you look at the forms or reports that the organization generates. So for example, in the property management firm, there's going to be things like leases or client applications when they register with you, or owner registration documents or property registration documents. Those are all going to be forms or reports that are maintained by the property management company. And you can get information from those reports that they contain data that you know is going to be stored in the database. And then there simply may be other sources of information about the enterprise, like on their website, you just read information about the enterprise, or they may already have existing file systems or an existing database or something, so that would give you information. So all these things you can see are inputs into the user requirement specification. And once you have that, then you're trying to reduce that to a set of relations. And as I said, most people will take a top-down approach to get the relations, and then they will use normalization to validate it. So approach 2 is the most common one, where we start with top-down modeling, and then as a check, we apply normalization to it. As an alternative, you could just start with normalization to begin with. And for those of you who are more bottom-up oriented, that can work as well. In fact, today we are looking at it exclusively from a bottom-up perspective. Okay, so here is what might happen if you simply take information from forms. Let's say that one of the pieces of information you have access to in the property management company is a staff directory. So the staff directory maybe lists the staff number, their name, their position, their salary, the branch number they work at, and the branch address. And that's contained in some file or printed somewhere. At any rate, based on that, you tentatively design a relation that looks like this, because that's the way the form or the directory was set up. And you call it the staff branch relation. Okay, so the first thing you should notice is there's redundant information here. So The branch address at 22 Deer Road is repeated twice. The branch address 163 Main Street, Glasgow is repeated 3 times. So there is a issue there. Also, the branch number is repeated multiple times, although that may or may not be an issue, but having the branch address done multiple times may be a real issue. So if I try to update, if the branch 5 moves to some new address, I'm going to have to remember to update that branch in multiple places here. So if branch B5 moves, I need to update the branch address for John White, but I also have to update the branch address for Julie Lee. And that could be an issue if I forget to update one of them, because then I'll have inconsistent information in the database. That is called an update anomaly. When you update one piece of information but forget to update another piece of similar information, and it creates a inconsistency. So we call that an update anomaly. Here's another issue. Oh, go ahead. Yes, go ahead.
Oh, I was just going to ask, did you say that position also had redundant data?
I did not. And the reason is that it turns out, we'll see that even though it's redundant here, it is not redundant with respect to the person. So we're going to find out that branch B05 is what determines the branch address, but it is the staff member that determines the position. So the fact that the position is duplicated in multiple places is actually not redundant. If John White is promoted to president, we don't have to update that information anywhere else.
Okay.
Okay, or if Ann Beach is promoted from assistant to manager, we don't have to update that anywhere else. So it's actually not a redundant piece of information here. I know it's a bit subtle, but hopefully as we go through this, it might get a little clearer.
That's because the position doesn't really depend. I mean, because if you look, manager has 2 different staff numbers and 2 different names. So the position itself doesn't really depend on any other attribute that's in there.
Yes.
Is that right? Okay.
Whereas here, if you look at the branch address, it's actually depending on branch number. It's always B5. B5 determines what the branch address is, or B3 determines what the branch address is. So here, that's kind of the problem, is that B3 163 Main Street is being repeated multiple times. So if the fact that Ann Beach was an assistant was repeated somehow multiple times in this relation, then it would be a problem.
That makes sense.
Okay. Okay, so that's one type of anomaly. It's called an update anomaly. There's another type of anomaly called an insert anomaly. Let's say that this is the only place where I am keeping information about branch addresses, and that I start building a new branch, but it doesn't yet have any staff. Nonetheless, I would like to record the fact that I have a new branch, say B10, going in at 1678 Cardiff Road. It turns out that I can't insert that tuple into this relation because it doesn't have any staff associated with it. And the problem is, if you look at what is the primary key for this directory, it turns out to be the staff number. That is the primary key, because it's really oriented toward keeping information about each staff member, and only secondarily is it concerned about the branch. But the problem is, if this is the only place where we're keeping branch information, we have no way of inserting a empty branch into this relation because the staff number can't be null. It's the primary key. And if you remember, entity integrity says that a primary key can't be null. So we call this an insert anomaly because there's no way to insert a new branch into this relation unless it has a staff member associated with it. So that is an insert anomaly. And then there's a third type anomaly, which is a delete anomaly. So if I delete Mary Howe from this relation, then I lose all information about branch B7. You'll notice there's no other tuple in this relation that contains information about branch B7. So if I delete Mary Howe, I end up deleting any information that I have about branch B7. So that's called a delete anomaly because I end up losing information when I do a delete. Okay, so that's just what is I'm showing here is different information or different anomalies. So this is another anomaly that I didn't mention. So another anomaly back here is if I change, let's say John White moves to branch B7, then I have to remember to also update John White's branch address to be 16 Ardagh Street in Aberdeen. So if I update the branch number, I also have to remember, to update the branch address. And if I don't, I'm going to have inconsistency because the branch address will no longer match the branch number. So that's another example of an update anomaly. Okay, so as I just went through, there's three types of anomalies that we could come up with. Modification means update anomaly. And it also turns out that anytime you have an assertion anomaly, you have a matching deletion anomaly. Because if you cannot insert an empty branch, it means that you will lose all information associated with that branch if you delete all the staff with that branch. So every insert anomaly has a matching delete anomaly and vice versa. So what we're trying to do with normalization is get rid of these kinds of anomalies. We want to eliminate the potential for these modification anomalies by only storing a descriptive attribute like branch address in one place. Turns out we can get rid of insertion and deletion anomalies by ensuring that only one entity is stored in each relation. So that's an important point. So the way we eliminate, so insert and delete anomalies arise when two or more entities are stored in the same relation. So normalization is going to ensure that we only store one entity per relation. Okay, so basically with normalization, it will ensure one entity per relation. So that's where you get your insert and your delete anomalies. Okay, and then your modification anomalies arise because a descriptive attribute is somehow repeated. Okay, and you saw two different ways that that happened back here. So one way was that we just had this branch address repeated multiple times, like 22 Deer Road was repeated multiple times. The other way was a little more subtle. It was linked. The descriptive attribute branch address was linked to another attribute so that when you change that other attribute, it needed to change as well. So that was kind of another kind of duplication that was going on. So normalization is going to attempt to put those descriptive attributes in just one place. So when we do normalization, we're trying to accomplish two things. We're going to try to ensure that when we decompose a relation into two or more relations, that you can combine those relations back to the original relation and not lose information. So that's called the lossless join property. And the way we essentially accomplish that is with foreign keys. So the foreign keys are what allow us to rejoin the different relations together to reform the original merged relation. And then the second thing we need to ensure as we do decomposition is we decompose a relation into multiple subrelations is to preserve dependencies. So for example, the branch address depends on the branch number. So we want to ensure that that dependency is preserved in one of the smaller relations. So a dependency is like a constraint. For example, branch number determines this branch address. So we want to ensure that any such dependency gets preserved when we decompose the relationship. Okay, so that's what normalization is trying to accomplish. So now we're going to move to how normalization works. And to do that, we have to start with an idea of functional dependencies, because that's what normalization is based on. So a functional dependency is some relationship among attributes. In ER modeling, we were concerned about relationships among entities. With normalization, we're more interested in relationships among attributes. And we say that if each instance of A uniquely determines a value of B, then we say that A determines B. And we call this a functional dependency. So if you look back here, you can see that branch number determines the branch address. So that would be a functional dependency. You can also see that the staff number is going to determine the staff name and the person's position, and perhaps it determines their salary or perhaps not. Okay, so we will get to that, but it certainly seems that a staff number determines a staff name, a position, and a salary. The reason I'm hedging that is it might be the case that we always say every position has a fixed salary. Now you can see that's not the case here because a manager, Susan, makes 24,000 and this manager, John, makes 30,000. But we might have some thing that says, okay, for every branch, that position has the same value. So for example, branch 5, all managers might make 30,000, in which case we would have a functional dependency that said that the branch number and the position would determine the salary. So we are interested in trying to identify these functional dependencies. And again, what it means is that each unique combination of values on the left side uniquely determines some value on the right side. Okay, so it's okay, it's for the reverse to not hold. So for example, coming back here, a staff number uniquely determines the branch number where the person works. But a branch number does not uniquely determine the staff number. You can see that B5 has both SL21 and SL41 working at that branch. So it doesn't have to, the reverse doesn't have to hold. A might uniquely determine B. So here, A might uniquely determine B, but the reverse doesn't have to hold. Okay, and that's the same thing they're showing here. A staff number uniquely determines the person's position, but the position does not uniquely determine the staff number. So you can't go the opposite way with that functional dependency. And you're going to hear us use the word determinant to refer to the left-hand side of an arrow. That so that's important, just as a terminology. But coming back, I'm going to give you a preview of things. Basically, every function, for the most part, as a general rule, so as a general rule, each functional dependency will result in its own relation. With the left-hand side, namely the determinant, being the primary and or foreign key. So that's just a general rule. There will be some exceptions to it, but this is a good general rule that each functional dependency that you identify will result in those attributes being in their own relation, and the left-hand side determinant being either the primary key or a foreign key or both. So functional dependencies are super important since they're essentially determining the relations. Okay, remember that I said we want to ensure these two properties. So the dependency preservation property is trivially enforced if each set of attributes in a functional dependency end up in their own relation, because that trivially preserves the dependency. And then the lossless join property gets preserved as long as the left-hand side is preserved in the original relation. So when we decompose, we're still going to have some attributes left in the original relation. And it's going to turn out that what stays in both the original relation and that what moves to the new relation is the left-hand side attribute. So the second thing I can tell you about decomposition, about normalization, is that when we decompose a relation using a dependency, the right-hand side attributes move from the original relation to the new relation. So one, the right-hand side attributes move from the original relation to the new relation, and the left-hand side attributes both stay in the original relation and are copied to the new relation. Okay, so this preserves lossless join. Whereas 1 and 2 together preserve the dependency, because both the right-hand side attributes and the left-hand side attributes end up in the new relation. So 1 and 2 together preserve the dependency. 2 preserves or enforces the lossless join by ensuring that the left-hand side attributes remain in both the original relation and are copied to the new relation. So questions thus far? Okay. So when you have a functional dependency, it exists only if it holds for all time. So you can't just look at the data to make that determination. You have to also use judgment. So if we just look at the sample data in that staff directory, it would appear that both the staff number determines the staff name and that the staff name uniquely determines the staff number. But if we think more deeply about it, we realize that in this world there are duplicated names, and it is quite possible that we will hire two people with the same name. As unique as Brad Vanderzanden might seem, I can Google me and there is another Brad Vanderzanden living in the US. I am not unique. So you can't guarantee for all time and for all data that the staff name will uniquely determine the staff number. So you can't just use your sample data to derive your functional dependencies. You can use the sample data to form a hypothesis about your functional dependencies, but then you need to verify that by talking to people in the company to verify that that really is a functional dependency, or just by thinking a little more deeply about it and saying something like, well, is it possible that we could hire two people with the same name, and realize that the answer is yes, you could. And therefore, this is not a true functional dependency. So the only one that really holds for all time is this one: staff number determines staff name. Then another characteristic of functional dependencies is that they need to be, the left-hand side or determinants need to be minimal. So you don't want extraneous attributes on the left-hand side. And we call this requirement a full functional dependency. So if the determinant is the minimum number of attributes necessary, then it's a full functional dependency. So for example, it is true that the staff number and the staff name uniquely determines a branch number. But this is not a full functional dependency because we do not need staff name in order to uniquely determine the branch number. All we need is the staff number to uniquely determine the branch number. So we would call this dependency a partial dependency because the determinant is not minimal. We can get rid of staff name and still uniquely determine branch number from the staff number alone. Okay, so this is a review slide. So characteristics of functional dependencies. It is a one-to-one relationship between the left-hand side and the right-hand side attributes. So for each unique set of values for the left-hand side attributes, there is exactly one set of values for the right-hand side attributes. So it is a function in the classical sense that it's essentially saying that you have a function where it is f of a equals b, and there is one and only one value of b for each value of a. Okay, the second characteristic is that it holds for all time. It doesn't just hold with the current set of data that we have, but it would also hold for any potential data that we would add or subtract in the future, in particular for any data that we would add in the future. And finally, every functional dependency, the determinant has the minimum number of necessary attributes associated with it. Okay, one important type of functional dependency that we will be concerned with is transitive dependencies. So they are dependencies where you have basically A determines B and B determines C, and therefore A determines C. And so if you're not careful, you might end up trying to write that A determines C and model that explicitly, but you don't want to do that because if you already have the fact that A determines B and B determines C. So for example, we know that staff number determines the branch number. And we know that the branch number determines the branch address. So it's also the case that the staff number determines the branch address, but we're not going to model that dependency because this is a transitive dependency that can be inferred from two other dependencies. So we don't want to explicitly represent transitive dependencies. Okay, so when we list our functional dependencies, we do not list transitive dependencies. Like A determines C, because we already know from these two dependencies that A determines C. So we don't explicitly represent transitive dependencies when they can be inferred from two other dependencies. Okay, so that's just, this slide just shows that dependency that I was already talking about. Here, staff number determines the branch number determines the branch address. So we're not going to explicitly show that the staff number determines the branch address. Okay, so now what I want you to do is take about 3 or 4 minutes and see if you can't identify the set of functional dependencies for the staff directory relation. And I want you to assume that the position held in the branch determines a staff member's position. So for example, all managers at branch B5 will earn the same amount of money. All assistants at branch B3 will earn the same amount of money. So just take a moment. I'm going to go back to slide number, whoops, don't want to show you that. Slide number 6. And I want you to take a few minutes to try to determine what you think are the functional dependencies here. So I'm going to give you about 3 minutes, and then I will show you what those functional dependencies are. Okay. So let me go through now what those functional dependencies are. Getting you to think about it was the main point of the exercise before I show them to you. So the functional dependencies are these. The staff number determines the person's name, their position, their salary, and the branch at what they work. The branch number determines the branch address. So you might have been tempted to put branch address here, but the fact that the branch number determines the branch address means that you should not put the branch address in this functional dependency because it's determined instead by branch number. You might not have gotten this one, but the branch address, because it has the city and a street address, that pretty much uniquely determines the branch number. So these two go both ways. Then I told you that the branch number and the position determines the salary, which means also that the branch address and the position determine the salary. So you got to be careful here. That's why I wanted you to go through this exercise. I think getting this one, the staff number, is fairly easy, although you might have included branch address here, which you shouldn't have. And branch number determines branch addresses might be easy. And I kind of gave you this one by saying that assume position and branch determine a staff member's salary. But branch address determining branch number and branch address and position determining salary, you might not have gotten. So you do have to think very carefully about what all the functional dependencies are and not just go for the obvious ones. The questions about these dependencies. Okay. So moving on, we have already discussed the importance of identifying the primary key for a relation. So normally, when you're doing that with functional dependencies, what you're trying to do is find a set of attributes that uniquely determine the values of all attributes in the tuple. And any set of attributes that can do that becomes a candidate key. So it's really the same idea as what you had for entity relationship modeling, is that any minimal set of attributes that uniquely determine tuples in a relation become a candidate key, and one of those will become the primary key. Okay, so for the staff directory relation, the staff number is one key. It turns out that there is no other set of attributes for the staff directory that could uniquely determine each tuple in the staff directory. For example, I could say the staff name, the salary, the position, and the branch number should uniquely determine the staff person, but it is just barely possible that two people with the same name work at the same branch in the same position and have the same salary. What are the chances of that happening? Infinitesimal, but not zero. And if it's not zero, then the potential for duplication exists. So it can't, the only potential candidate key for the staff directory relation is staff number. Okay. And this slide essentially is just saying that this is the case, that when you claim that your left-hand side is a primary key or a candidate key, then all the attributes that are on the right-hand side are functionally dependent on it. Okay. So now we have set the basis for doing normalization. We have talked about what we want to accomplish, which is we want to ensure that each entity is in its own relation and that descriptive attributes are not duplicated. And the way we're going to do that is by identifying functional dependencies. And then we're going to use those functional dependencies to decompose relations into subrelations. And when we've identified our primary keys, we have typically identified unique entities. So generally, primary keys are, each primary key is going to be associated with a different entity. So we've laid the fundamentals. Now we're ready to talk about kind of the mathematical basis for it. Now, we only have a few minutes left, so I'm just going to lay out the general algorithm, and I'll get into the specific algorithm on Thursday. So first of all, as normalization proceeds, you get progressively more restricted relations that are less vulnerable to update anomalies. So you're going to see that we have a variety of normal forms. So the least restrictive is first normal form, then the next most restrictive second normal form, third normal form, Boyce-Codd normal form, so on and so forth. In this course, we're only going to be concerned with getting up through third normal form. The book talks about Boyce-Codd normal form. I'm going to give you an example of a situation where third normal form is not in Boyce-Codd normal form, but Boyce-Codd normal form is a fairly rare situation. It is almost always the case that if a relation is in third normal form, it is also in Boyce-Codd normal form. The homework assignments and the tests will always stop at third normal form, but I will at least talk about Boyce-Codd normal form in this course. So what happens is we start potentially with relations that are unnormalized. And what we want to do is successively move them into first, second, and then third normal form. And by the time we have them in third normal form, we have eliminated almost any update anomaly of consequence. The remaining ones are so esoteric that you might have so to get to third normal form or Boyce-Codd normal form, you may have done 20% of the effort to get 99% of the benefit. And to get to fourth normal form and fifth normal form is almost like the proverbial using the remaining 80% of your time to get 1% of benefit, and it's just not worth it. So we are basically going to use our functional dependencies to get us to go through these different normal forms. So we're going to identify essentially 3 different types of dependencies. We've already seen one, which is transitive dependencies. There's also going to be a type of dependency which we'll call a partial dependency. And finally, there's going to be what I would call the candidate key dependencies. And each of those we're going to be able to use to set up relations. So Thursday, we're going to go through the algorithm for normalization, and then we'll also go through a case study so that you can get some practice for the homework. Again, if I don't go through that case study, many of you will struggle on the homework. I'm also going to look at the quiz for today to make sure that you can answer the questions. If you can't, I will defer the quiz. So I will post something later today to say whether you need to finish today's quiz or not, because I did not get through the complete lecture for today. So with that, I'm going to let you all go. I will see you on Thursday, where we'll finish this discussion of normalization and go through the case study.